You type modern home office into an AI image generator. The progress bar hits 100%. And like at first glance, the result is stunning.
Oh, yeah, the lighting is usually photorealistic.
Right, the textures are perfect, but then you look a little closer, and you realize the desk chair in the corner has 5 legs.
Or the shadows are completely backwards.
Exactly. The shadows from the window just do not align with the lamp on the desk. And that motivational poster on the wall is written in what looks like alien hieroglyphics.
It is the quintessential AI double take.
Yeah.
The aesthetic illusion is flawless, but the physical reality falls apart the absolute second you scrutinize the actual geometry.
Which is incredibly frustrating. So today we are doing a deep dive into a state-of-the-art research paper that dissects exactly why that specific illusion shatters, and more importantly, how a team of researchers has engineered a way to fix it.
Yeah, they fundamentally changed the approach.
Right. We are looking at a system called JoyAI-Image, which was developed by the Joy Future Academy at JD. Our mission on this deep dive is to explore how they are finally teaching artificial intelligence to genuinely comprehend 3D space, physics and complex layouts. It is a monumental leap toward true spatial intelligence.
What's fascinating here is that the underlying breakthrough goes far beyond just generating prettier pictures. The JoyAI-Image architecture is built entirely around establishing a bidirectional loop.
A bidirectional, explain what that means in this context.
Well, historically, the AI community has treated image understanding, so like computer vision models, and image generation, like diffusion models, as completely separate disciplines.
Right, they were built in silos.
Exactly. But this paper integrates them so aggressively that the act of understanding a scene and the act of creating a scene actually feed into and refine each other actively.
Which honestly feels like the missing link in how we interact with these tools. I mean, the math in this paper is dense. We are looking at massive parameter counts, multidimensional tensor fusions, complex geometric mapping.
It is a lot of math, yeah.
But the mechanical logic driving it is something you can really visualize. So let's start at the root of the 5-legged chair problem. It essentially boils down to flatness. Current generation models treat images as flat 2D canvases rather than viewports into a 3D world.
That is the core issue, yes.
But right out of the gate, I have to push back on the premise that this requires some totally novel architecture. Because usually in modern AI, the answer to every problem is just scale it up, feed it more compute, feed it more data.
That is the usual playbook.
Right. So if we train a model on 10 billion pictures of living rooms, shouldn't it implicitly figure out how chair legs work just through sheer volume of exposure?
You would assume that, right? But scaling up 2D data just makes a highly efficient 2D interpolator. Traditional diffusion models are acting as statistical pattern matchers on a flat coordinate plane.
Okay, so they aren't actually learning what a chair is.
Exactly. If you feed them 10 billion images, they learn that the cluster of pixels representing a chair seat is statistically likely to have vertical clusters of pixels called legs extending downward. But they never learn what a chair physically is as an object occupying a volume of space.
They're just optimizing for pixel probability.
Precisely. Not geometric truth.
Okay, that makes total sense. It's like someone who has read a million encyclopedias about a bicycle, but has never actually ridden one, or even walked a full circle around one.
That's a great analogy.
They know exactly what a bike should look like from a strict side profile, but they lack the mental 3D blueprint to understand how the pedals on one side mathematically connect to the gears on the other.
Right, because they've only ever seen the flat representation.
So how does the JoyAI image architecture force the model to build that mental 3D blueprint?
Well, it abandons the monolithic structure entirely. Instead of one massive model trying to guess pixel patterns, JoyAI-Image couples two highly specialized systems that communicate through a really rich shared interface.
Okay, 2 systems. What are they?
You have a multimodal large language model, or an MLLM. Specifically, they used Qwen3 VL8B instruct, and that acts as the cognitive brain. Then you have a multimodal diffusion transformer, or MMDIT, acting as the generation engine.
I want to pause on that communication interface for a second, because older diffusion models also use text encoders to talk to the image generator. So what makes Qwen3 VL so fundamentally different as a cognitive brain in this setup?
The critical difference is the depth of the conditioning signals. In a standard setup, the language model passes a relatively shallow embedding string, like you prompt draw a cat on a bike and it passes that basic concept.
Just the nouns, basically.
Yeah, pretty much. But the MLLM in JoyAI-Image is designed to provide semantically rich and spatially grounded signals. It doesn't just parse the nouns, it parses the spatial intent, the intended layout, the implied physics, and passes those complex insights down the pipeline.
So it is handing over a literal architectural blueprint, not just a grocery list of objects.
Precisely the way to think about it. The generation engine, the MMDIT, then uses a dual-stream architecture to fuse that cognitive blueprint with visual data. And this visual data isn't raw pixels, by the way.
Well, it's not. What is it?
No, it comes from a variational autoencoder, or VAE. The VAE compresses the raw visual chaos of an image into a latent space. It's a mathematical coordinate system where visual concepts are dense and structured.
Oh, okay.
So the MMDIT operates entirely within this latent space. It takes the spatial blueprint from the MLLM, grabs the visual building blocks from the VAE, and iteratively denoises them to construct the final image.
Okay, so the brain maps the physics and the hands mold the clay in the latent space.
Exactly.
But Oh Brilliant Brain is completely useless if it doesn't possess actual knowledge of how physical reality operates.
Right.
To get that bidirectional loop started, you have to inject 3D awareness into a system that only consumes 2D files.
Right, which is the hard part.
And the researchers built a massive data engine to do this, called Spatial. But how do you artificially teach space to a machine using flat data? Like, didn't we already feed AI all the images on the internet?
We did, but seeing isn't understanding. You have to force it to perform spatial reasoning tasks on an unprecedented scale. OpenSpatial synthesized 3 million entries of spatially grounded Q&A data.
3 million.
Yeah, but the ingenuity lies in how they actually sourced it. Since we lacked 3 million perfect 3D LiDAR scans of human environments, they relied on a 3D lifting mechanism applied to unconstrained 2D web videos.
Okay, let's unpack that lifting mechanism. I imagine it works somewhat similarly to parallax, right? Like when you look out the window of a moving train, the trees near the tracks blur past instantly. But the mountains in the distance barely seem to move at all.
Yes, exactly.
And by measuring the difference in those speeds, your brain naturally calculates depth. I'm assuming the AI is doing the same thing mathematically across video frames?
That is the exact mathematical intuition. They take regular video footage of someone walking through a room or panning a camera. Algorithms track the relative motion vectors of objects across the frames, integrate depth mapping, and calculate that parallax effect you just described.
Wow.
Yeah, by crunching those frame-by-frame changes, the system can lift the flat pixels of the video into accurate 3D bounding boxes. It basically reverse engineers the volume of the room.
That is incredible. And once you have a mathematical 3D box of a room, you can generate basically an infinite number of tests for the AI.
Which is exactly how they built the OpenSpatial training curriculum. They focused on 5 foundational spatial capabilities. First is spatial measurement, where the AI must determine absolute distances. It answers questions like, how far is the edge of the cabinet from the bed in meters?
Physical measurements, got it. What's the second one?
Second is spatial relationship, which requires relative positioning from a specific vantage point, such as is the plant to the left or right of the television based on the current camera angle.
Okay, and the third capability, camera perception, that would involve tracking how that vantage point is actively shifting through the space.
Yes, exactly. Understanding trajectory and lens distortion. The fourth is multi-view consistency. This is recognizing that the back of a sofa belongs to the same object as the front of the sofa that it saw 3 seconds earlier.
Object permanence, basically.
Exactly. And finally, there is scene-aware reasoning, which forces the model to synthesize all this data to navigate or plan a route through the newly mapped environment.
It makes me think about the innate intuition required to parallel park a car. You aren't doing active calculus to measure the distance between your rear bumper and the curb. You rely on an internalized spatial map and multi-view consistency based on just a few glances in your mirrors.
That's a great way to put it. JoyAI-Image is learning that identical physical intuition, and the benchmark testing actually validates that intuition.
How so?
They ran JoyAI-Image through spatial understanding evaluations that were specifically designed to trick standard models with complex physical logic and occlusion, and it achieved an average score of 64.4.
Wow.
Yeah, that dramatically outperformed previous open-source models, and it competed aggressively with massive proprietary closed-source models. The MLLM has genuinely acquired a mental map of physical volume.
And that macroscopic understanding of room volume directly influences microscopic 2D layouts. Which brings me to the absolute acid test of an AI understanding spatial layout on a flat plane.
Typography.
Yes, typography. Okay, let's unpack this. Because going back to our initial frustration trying to generate spelled text with a diffusion model has historically been like trying to forge a document while looking through a kaleidoscope.
It's nearly impossible for them.
Right, the letters bleed, the E morphs into a C if a shadow hits it wrong. So how does this architecture solve the alien hieroglyphics problem?
Typography is brutal for diffusion models because it demands pixel-perfect spatial arrangement. Language has absolutely zero tolerance for geometric interpretation.
Right, an A has to be an A.
Exactly. To conquer this, the JD researchers engineered an unforgiving, OCR-aware captioning pipeline. They realized that simply prompting the model with the text string just wasn't enough.
It's the counterfeiter problem again. Telling a counterfeiter to just draw a $100 bill doesn't work. You have to give them the exact microscopic printing plates.
Right.
How granular did they get with these OCR descriptions to give the AI those plates?
Granular to the level of structured JSON coordinates.
Wait, really?
Yeah. During training, they ran a specialized OCR model over their image dataset to extract the exact text tokens visible on storefronts, posters, menus, everything. Then they fed those tokens into a multi-level captioning system.
What are the levels?
They generated short captions for basic context, long captions for detailed narrative, and extended long captions that specify the material, texture, and lighting of the object holding the text.
But the real breakthrough is the structured captions, correct? Where they map the text to actual screen coordinates.
Yes, exactly. The structured captions break the image down into a JSON format that provides precise bounding boxes for every single character or word token detected by the OCR.
Oh, wow. So it's a strict grid.
Yes. By forcing the MNDIT to map the raw OCR text tokens to these dense, mathematically rigid layout blueprints, the AI internalizes exact typography. It learns precisely how the letter A physically occupies a defined coordinate space relative to the letter B on a curved sign.
The quality control on that data must be staggering, though. Because if the captioning model hallucinates a single word or even slightly misaligns a bounding box, the model learns a permanent typo.
The filtering was absolutely ruthless. Any ambiguity, any hallucinated translation in the OCR pass resulted in the data being immediately discarded. But that uncompromising approach is exactly why it works.
Did they benchmark the text generation, too?
They did. On the long text bench evaluation, which specifically measures prompt adherence for complex typography, JoyAI-Image scored 0.963 on the English benchmark.
0.963. That's almost perfect. And the cascading effect of that blueprint is that the model's performance isn't locked to just the Latin alphabet, right?
That's a fascinating consequence of this method. It also scored a 0.963 on the Chinese long text benchmark.
Wow, exact same score.
Yep, because it learned the spatial geometry of character placement rather than just memorizing English word shapes. It handles entirely different, highly complex typographic structures with identical precision.
That makes total sense.
And here is where we see the bidirectional loop explicitly in action. Because the cognitive brain understands the spatial arrangement of text flawlessly, the generation engine can draw it flawlessly, which in turn gives the cognitive brain perfect synthetic data to reinforce its understanding.
That loop is incredibly elegant. But I want to pivot to a completely different kind of data problem they had to solve, which moves us from the mechanics of spelling to the overall artistic scope of the model.
Ah, the long tail problem.
It's exactly the long-tail distribution bias. Let's be honest. The internet's image data is overwhelmingly composed of selfies, coffee cups, and cats.
Lots and lots of cats.
So many cats. And if you just scrape the web and feed it into an AI, it becomes a savant at drawing cats, but completely collapses when asked to generate a rare architectural style from, say, the 14th century.
The long tail problem plagues literally every foundation model. The AI optimizes for the dominant patterns in its training distribution and essentially ignores the rare edge cases. It results in a model with a massive blind spot for cultural, artistic, or historical diversity.
So how do you force the model to be a well-rounded student? How do you make it care about the rare data at the tail end of the curve?
You have to perform a surgical intervention on its data diet, which requires a massive semantic taxonomy. The researchers constructed a categorization tree containing 285,000 distinct leaf nodes.
Wait, 285,000?
Yeah, representing 285,000 unique concepts, objects, and styles. They then mapped their entire training data set to these specific nodes.
That is essentially enrolling the AI in a comprehensive art and history curriculum, rather than just letting it doom scroll social media all day.
Exactly.
But once they map the data to the 285,000 concepts, how do they actually alter the distribution?
Through aggressive mathematical rebalancing. When the taxonomy identified a concept node overloaded with tens of millions of images like modern sedans or domestic cats, the researchers deliberately downsampled it. They restricted the model's exposure.
And for rare stuff.
Conversely, when the taxonomy identified rare categories with sparse representation, they boosted them. By flattening the distribution curve, they forced the model to allocate compute and learning capacity to the rare concepts just as heavily as the ubiquitous ones.
So the model is forced to build robust, latent representations for everything, not just the low-hanging fruit.
Exactly.
Okay, so we've explored how JoyAI-Image constructs a 3D mental model, how it masters precise typographic layouts, and how it ensures an encyclopedic visual vocabulary. Let's bring all this together to examine what happens when you want to manipulate an existing environment.
This is my favorite part.
Here's where it gets really interesting. Because if you take a standard AI image editor today and ask it to move the camera 45 degrees to the left, the diffusion model usually just melts the background into a smeary, hallucinatory mess.
Right, because it doesn't know what is hiding behind the foreground objects.
Exactly. So how does JoyAI-Image execute spatial editing without breaking the physics of the photo?
If we connect this to the bigger picture, this is where the bidirectional loop between perception and generation reaches its peak utility. The JoyAI team calls this capability novel view-assisted reasoning.
All right. Novel view-assisted reasoning.
Remember the open spatial engine and the parallax 3D lifting we talked about? They supercharged that capability by pairing it with a million-scale data set of multi-view images rendered in Blender.
So they fed it synthetic 3D scenes where the absolute truth of the geometry is mathematically known.
Completely known and mathematically perfect. The model analyzes millions of examples of the same complex scene rendered from a full 360-degree sphere of camera angles.
Oh, wow.
Consequently, you no longer have to use vague prompts like, make it look like we stepped to the side. You can issue strict geometric commands. You can literally instruct the model camera rotation, yaw, 0.0 degrees, pitch 60.0 degrees.
You're literally treating the 2D photograph as a video game environment, grabbing the virtual joystick and panning the camera.
Yes, exactly.
But how does the architecture process a command like pitch 60 degrees without destroying the image?
Well, the MLLM, the cognitive brain, reads the geometric instruction and cross-references it with the source image simultaneously. It serves as an intent explanation mediator. So it mathematically projects what a 60-degree pitch shift actually means for every object, every shadow, and every occlusion in that specific scene. It maps the new spatial coordinates. Then the MMDIT generation engine receives those coordinates and executes the precise transformation in the latent space.
It repaints the perspective based on the math, meaning the background stays perfectly anchored relative to the foreground.
Because the model intrinsically understands depth mapping now, and this novel view reasoning extends to object manipulation too, you can command it to move a lamp from a desk to the floor, and it will calculate the new shadow trajectory automatically.
That is wild.
It enables flawless IP-preserving edits where a specific character's design remains perfectly consistent even as you dynamically alter their pose and lighting within a complex environment.
The implications of this are just huge.
Yeah.
Every time you make a spatial edit, you're engaging that bidirectional loop.
That is the ultimate takeaway of the entire architecture. The precision of the spatial understanding enables the precision of the image edit. But equally important, the execution of those precise spatial edits generates internal feedback that continuously refines the MLLM's understanding of the world.
Which is laying the infrastructural groundwork for what the field refers to as world models.
Exactly.
A world model being an AI that doesn't just generate pixel arrays, but actually simulates the physical physics of reality.
Think about the frontier of vision language action systems, specifically robotics. If you drop a humanoid robot into your kitchen, it requires a robust world model to function.
Right, they can't just bump into everything.
No, it needs to process a flat 2D camera feed and instantly comprehend the 3D volume of the kitchen island, the required reach distance to the refrigerator handle, and deduce what the unseen side of the room likely looks like. JoyAI-Image proves that perception and generation can be unified into a single framework to achieve that exact type of spatial reasoning.
It really is a massive paradigm shift. We've covered a lot of ground today. We started with the frustrating reality of five-legged chairs and kaleidoscopic text, exploring how JoyAI-Image dismantles the flatness problem by pairing the Qwen3VL cognitive brain with the MMDIT generation engine.
Yeah, we unpacked a lot.
We look at how the open spatial engine used parallax mathematics to lift 3D bounding boxes out of 2D video, teaching the AI spatial measurement and multi-view consistency. And we saw how OCR-aware JSON captioning forced the AI to master the strict geometric constraints of typography.
Not to mention the semantic taxonomy rebalancing.
Right, which prevented it from just becoming a savant at drawing cats. And finally, we saw how novel view reasoning allows you to mathematically rotate a camera inside a flat photograph without melting the physics. We are no longer dealing with simple image generators. We are interfacing with physical reality simulators.
And if we extrapolate the trajectory of foundation models like JoyAI-Image, it leaves us with a profound implication about the nature of media itself.
Oh, I like where this is going. What is the implication?
If an AI architecture is reaching the point where it can perfectly compute the 3D physics, lighting, and occlusions of a single 2D photograph, well, it means the model can seamlessly compute and generate the geometry of what was standing behind the camera, or what was hiding just around the corner out of frame.
Oh, wow. That completely changes the definition of a photograph.
Consider the impact on our personal archives. What happens to our fundamental concept of a memory when we possess the computational ability to flawlessly re-render a moment from our past, exploring it from vantage points and angles where no human ever actually stood?
That is slightly terrifying, but deeply fascinating. It's an entirely new way to conceptualize our relationship with history. Thank you for joining us on this deep dive into the JoyAI image research. The next time you edit a photo, remember the spatial leaps making it possible. Keep questioning the mechanics behind the technology you use and stay insanely curious.